Greetings, everybody. We're going to do part 2 of solving polynomials algebraically. And in this one, we're going to focus a lot on the quadratic formula. And let's go ahead and talk about that for a minute. Now, first of all, what is the quadratic formula? Well, basically it states that if I have an equation of the form ax squared plus bx plus c equals 0, standard form for a quadratic equation, I can find the zeros, the roots, the x-intercepts, whichever you wish to refer to them as, by using the formula x equals negative b plus or minus the square root of b squared minus 4ac. And there's something special about this b squared minus 4ac we're going to talk about here in a little bit, all over 2a. It's actually something that I actually like to do as a song. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You may have heard that in your algebra classes as well. I'm kind of contagious that way. But it's an effective way to help memorize it. So, solve it using the quadratic formula. So, first of all, I need to rewrite it. Quadratic formula works when your parabola is equal to 0. So that's where we want to start. And then from there, it's just your x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, in which a is 1, b is 7, and c is negative 18. You just take those three values and plug them into there, and you'll get something like that. So instead of saying negative b, we say the negative of 7 plus or minus square root of b squared is 7 squared minus 4 times a times c, which is not 18, but rather negative 18, all over 2a. So just fill in. A lot of times what I like to do is even this. I'll just go negative b plus or minus square root b squared 4ac all over 2. I'll just write it and I'll just leave the blanks in there and then just fill in based on your a's, b's, and c's. But you don't have to do it that way. It's just, I found it to be pretty effective. Now, it is a longer method. That is the one drawback of it, but what's good about it is that a lot of stuff doesn't factor, and so if it doesn't factor, you can't solve it by factoring. Quadratic formula, as well as like completing the square, will solve any quadratic, whether it factors or not, whether the answers are imaginary, real, really doesn't matter. So from here, we clean it up a little bit. I get negative 7. 7 squared is 49. Negative 4 times 1 times negative 18, I believe, is positive 72. So I get something like that. And then if you work on the inside here, 49 plus 72, I believe is 121. So I get 7 plus or minus root 121. And that makes 11. So I get two answers. One is that it's equal to 7 plus, the other that it's 7 minus 11, and then you just work it out. Negative 7 plus 11 is 4 divided by 2. Negative 7 minus 11 is negative 18 divided by 2. You get the answers 2 and negative 9. Now again, I would have been much happier solving that at the beginning by factoring. It's faster for me, but this works. Okay, let's try this one out. Again, to use the quadratic formula, I need it to equal 0. So I'm going to move the 10x over here. So my a is 1, my b is 10, my c is 8. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And then I just plug in. Every A becomes a 1, every B a 10, every C is an 8. And I doubt you guys need a whole lot of help on this method. I'm sure you're probably pretty good at it by now. But again, you do a little more work on it. The 10 squared is 100. The negative 4 times 1 times 8 is negative 32. And when you put it all together here, take your 100 minus 32, you get 68. And then you separate that into two parts, either negative 10 plus or negative 10 minus. I know some people would let you leave it that way. I'm going to go one step further. I can actually break down that square root of 68. That's what 2 and 34, 2 and 17. So the pair comes out. So technically I could write this as negative 10 plus 2 root 17 over 2 and negative 10 minus 2 root 17 over 2. And hopefully you see that this 2 does go into every term. So technically my answer would be negative 5 plus root 17 or negative 5 minus root 17. Or if you wanted to consolidate them all together, you could just say that x is negative 5 plus or minus root 17. And that's pretty much how your quadratic works. So I want to do this. In both videos, we talked about doing the quadratic. We talked about solving it in a, using factoring, using completing the square. Here we just talked about doing the quadratic. So I want to show that we can do this in multiple ways, and that I don't know if one way is necessarily any better or worse than the other. It's kind of what you see. So the big picture I want you to understand with this problem and why I wrote this problem is that I want you to understand that whether I solve by factoring, whether I solve by completing the square, or whether I solve by the quadratic formula, it's not going to change what the answer is. I'm going to get the same answer regardless of the technique I choose, because the solutions or the zeros to this problem are the zeros to this problem. They're not going to change just because you change methods. So I just want you to understand you have more than one option as to how you solve. So we'll start with factoring. Again, this is kind of my go-to. It's short, it's fast, it's easy, at least for me. X and x will make the x squared. 22 makes a positive 9. How about plus 11 and negative 2? Yeah, that'll do it. Then I take x plus 11, set it equal to 0, using my zero product property. Also the x minus 2 equals 0. So I get an answer of negative 11 and positive 2. Now the cool part out of this is when I do the other methods, I had darn well better get these same answers. Otherwise, there's an error in my computation. So let's take that same problem and do it by completing the square. Again, completing the square, I want the x's all by themselves. And I'm going to have to add something to that side so that it factors as a something squared. And then when I bring the 22 over by doing plus 22 and plus 22, and then I'm going to have to add that something. So let's find the something. Remember, to find the something, you take b over 2 and square it. There's my b. So I take 9 over 2 and square it, which is 81 over 4. Again, for those of you that love decimals, I believe that is 20 and 1/4 or 20.25, as you will. I'm just going to leave it as is. Let's try that again. And I know I'm going to need common denominators, so I'm going to multiply by 4 over 4. So that's going to make, let me see, 22 times 4, 88 over 4, plus 81 over 4, which is 169 over 4. Now, again, you say, I can't factor this. This is hard. No, remember, when you take the b over 2, which in this case is a positive 9 over 2, that's your factors. The b over 2, the 9 over 2, that's what goes here to make it factor. These two multiply to make 81 fourths. 9 halves and 9 halves makes 18 halves, which makes 9. So I get x plus 9 halves squared. We square root. Again, I'm looking for two answers, so although the square root of this is just 13 halves, and we'll talk about that in a minute, to get my two answers, I need to go plus minus. So why is the square root of that, of 169 over 4, 13 halves? Well, because if I take the square root of the top, 169, you can do it on a calculator if it makes you happy. If you want to check my work, square root of 169 is 13 over square root of 4, which is 2. And then I break it into two parts. One is that x plus 9 is the positive 13 halves, or my other choice is that x plus 9 is my negative 13 halves. And let's rewrite that 9. You do know that 9 is the same as 18 halves, I hope. So really this is like saying x plus 18 halves equals 13 halves. Okay. And then here this would be the same as saying x plus 18 halves is negative 13 halves. Now some of you I know are tripping and you're saying, I thought we got negative 11 and 2 last time. This doesn't look like it's going to give me that. Let's see what it gives me. Negative. Okay, I did do something really remarkably dumb here. Oh my gosh. Please help me. It's not 9, it's 9 halves. Again, that's where I told you, if you don't get the answer you got by doing it the other way, then you did something goofy. Apparently, I decided to do that. It wasn't 9, it was 9 halves. So that's 13 halves minus 9 halves is 4 halves, which is 2, which is one of the answers we got the other way. Negative 9 halves here. Negative 13 minus 9 is negative 22 halves, which gives me an answer of negative 11. So, yeah, eventually, if I were to actually write the problem correctly, that might not, might work a little better, but same answer. And then lastly, the quadratic. So it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So there's my b's. A, c is negative 22. There's my b, a is 1, and then all over 2a. So I get negative 9 plus or minus 9 squared is 81. I have a negative 4 times 1, which is negative 4, times a negative 22, which is going to be plus 88, all over 2, which is negative 9 plus or minus square root of 88 and 81 is 169. We dealt with that earlier when we were doing the completing the square, which gives me negative 9 plus or minus. Again, root 169 is 13 all over 2. So my two answers are negative 9 plus 13 over 2, or Negative 9 minus 13 over 2. Negative 9 plus 13 is 4 halves, which gives me an answer of 2. Negative 9 minus 13 is negative 22 halves, which gives me an answer of negative 11. So again, what I hoped you saw here is that regardless of which method you choose, I get the same answer. So let's talk the discriminant. Believe it or not, let's go back a little bit here to where, let me find it here. Almost there. Here we go. When I talked about this b squared minus 4ac, that is what's called the discriminant of a quadratic formula. You say, well, big whoop-de-doo, what does that do for me? Well, I'm going to show you what it does for you. It actually makes it so that you can know the answers or what type of answers you're going to get before you get them. So if you want to write down this table, if that helps you, so be it. So if the discriminant value, the b squared minus 4ac, is greater than 0, which is positive, you'll get two distinct or two different real numbered answers. If the discriminant is equal to 0, you get one real solution. And if b squared minus 4ac is less than 0, you get no reals, or you could say I get two complex or two imaginary solutions, if you will. And let me show you, rather than just here memorize the table, I'm going to show you why. So again, I'm not looking to solve this particular problem. I just want to know how many solutions it has and what type are they. So I'm going to refer back to here. I need to find b squared minus 4ac. So to do that, first thing I got to do is I got to make this equal to 0. So I'm going to move the negative 4x and the negative 4. So I'm going to get x squared plus 4x plus 4. Now I do my b squared minus 4ac. A is 1, b is 4, c is 4. So I get 4 squared minus 4 times 1, which is a, times 4. 16 minus 16, I get 0 for my discriminant. And if you look back, when b squared minus 4ac is equal to 0, I get one distinct real solution, or you could say that you get one real solution with multiplicity 2. That's kind of how I like to write this. You might say, what in the name of all that is holy is multiplicity 2? What does that mean? Well, I'm going to show you. Again, I guarantee I'm going to get one answer. Now you might say, but wait a minute. You told me that if the highest power is 2, I'm going to get 2. That's what this multiplicity means. It basically means I get one distinct answer, but I'm going to get the same number twice. So let me show you how it works. So if I were to take this as it is, so if I were to take this equation here, x squared plus 4x plus 4 equals 0. I mean, I know I can solve that by factoring really easy. That's x plus 2, and then you set it equal to 0. And then when you solve, when you subtract 2, I get an answer here of x is negative 2, and then here I get the same thing. Is that even possible? It's very possible. So let's kind of digest this for a minute. So what I get when this discriminant is 0, although there are 2 answers, which I told you should get because of the highest power of 2, I really only have 1 number, and they are real, they're not imaginary. I have really 1 answer, but I got the same one twice. That's what this multiplicity means. Now you might say, okay, let's take this next level here. So let's go here. So let's say I had this. So let's say it was x squared plus 4x plus 4 equals 0. And let's say I just called it like f of x. Again, we said our zeros were that I got x equals -2 with multiplicity 2. Say, I thought zeros are when the y is 0, it's like the x-intercept, it's where it crosses the axis. It is. So when you get this, when you get that b squared minus 4ac equals 0, and I tell you that you really get just 1 answer with a multiplicity of 2, what that means is you say, well, I thought the zeros are where it crosses. It does. You say, so then how does that, hang on. How does that play out? Well, what it means is that I get this 0 right here. What it means is that I get an answer like that. This occurs, this multiplicity of 2 happens when your discriminant is 0. And it also means that, graphically speaking, that is where your vertex is actually on the x-axis. Okay. Again, I'm not looking for what are the solutions. I just want to describe them. I want to know what kind of answers I'm experiencing. So my A is 1, my B is 1, my C is 1. So I'm going to find my discriminant, b squared minus 4ac. So b squared is going to be 1 squared minus 4 times a is 1 times c is 1. So that's 1 minus, oops, that's a really ugly one. Okay, that's an uglier one. 4 times 1 is 4. This gives me a discriminant of -3. Now again, if we go back, we said that if the discriminant is negative, I'm not going to get any real numbers. I'm going to get those 2 complex answers. I'm going to get like a plus bi and a minus bi. I think I'm going to get 2 answers that are conjugates of each other. That's what I believe is going to happen here. So let me show you how that works out. So again, I'm going to take that equation. I'm going to start it from scratch. So x squared plus x plus 1 equals 0. And this time, since it's not real, I don't get real answers, I'm not even going to try to factor it because I know it won't factor. So I'm just going to go x equals -b plus or minus, well, you know the drill. I think I've probably hurt your ears enough with song already. At one point, I used to sing very well, but you'd be surprised what 32 years of teaching and then coaching wrestling for 13 years can do for your voice, your vocal cords. It ain't good, let me put it that way. So my b here is 1, so I get negative of 1. Here's the cool part. We've already found this. We found b squared minus 4ac already. That gave us -3, so I'm not going to do it again. I've already done it once. And then 2 times a gives me -1 plus or minus over 2. Remember that a square root of a negative is I, like that. So you say, well, how do I reduce that? Well, you don't. That's it. I mean, you could say it's -1 plus I root 3 over 2 as one answer, and then the other is -1 minus I root 3 over 2 for the other. If you wanted to say it like that, fine. Otherwise, I'm okay like this. But again, what did I get? I got an a plus bi. I got 1 imaginary or 1 complex solution. And then a minus bi. Granted, they're over 2, but still, I got 2 complex solutions. Or you could say they're not real because of this I. Why did that happen? How come that works like that? Well, here's the idea. The b squared minus 4ac, your discriminant here, it's what's inside of the square root. And if that's negative, remember how we said that my b squared minus 4ac was negative 3? What that means, if you're doing the quadratic, you're going to be square rooting a negative number, which is why you get the two complex answers. So what would something like that look like on a graph? So you say, if the zeros are the solutions, they're the x-intercepts, what does it look like if they're imaginary? How do you graph imaginary zeros? Again, I don't know exactly what this graph looks like, but it looks, my guess is something like this. You're going to have a parabola that never touches the x-axis. Could look like that. It could look like this, like this. I mean, it could like a lot of different things, but basically the scenario is you get a parabola that never crosses the x-axis, which is why your solutions are not real. They're complex. And then this one, again, how many solutions, what type? I'm going to jump on the bandwagon here for my discriminant. So that's b, which is negative 7 squared, minus 4ac. A is 2. C is negative 15. It's 49. Negative, negative will make a plus. 15 times 2 is 30. That's 120. Yeah. Which makes 169. And since that is greater than 0, last time I checked 169 was greater than 0, that means I'm going to get two reals, which are not multiplicities. They're going to be two distinct different reals. So since b squared minus 4ac is greater than 0, you get two distinct, meaning different, distinct real solution, or real zeros. And you know what? How about we just play with it and find out? Again, I know when I'm doing the quadratic here, I know there's a b squared minus 4ac. We've already found it's 169, so I'm just going to ride that train and not calculate it again. So it was, what was it? 2x squared minus 7x minus 15. So I get x equals negative, b is negative 7, square root of, oh, we already found out that b squared minus 4ac was 169. We already did that, so there's no need to do it again. Negative of negative 7 is 7. Square root of 169 is 13. All over 4 here. And then easy peasy. 7 plus 13 over 4. 7 minus 13 over 4. 20 over 4 is 5. And 7 minus 13 is negative 6 over 4, which is negative 3/2. So what did I get? One real, two reals. One other thing I didn't tell you, but I want to. Another thing that the discriminant does is this. If b squared minus 4ac, if your discriminant is a perfect square, then you can factor the polynomial or the quadratic. Say perfect square, yeah, numbers like 1, 4, which is like 2 squared, 3 squared is 9, 4 squared is 16, 9 squared is 81, like that. So like here, when we got This b squared minus 4ac is 169, which is a perfect square. That tells me if I wanted to, rather than doing the quadratic, I could have just factored factors of 13 that differ by 7, be 5 and 3, and minus plus. It's going to give me an answer of negative 3/2 and 5. Same answers I got here. So if it's a perfect square, then you could have factored it. Little thing I wanted you to know. Here, we got a discriminant of negative 3. That is definitely not a perfect square. This is not a problem you want to factor. This one, it was 0. Is 0 a perfect square? Yeah, it's 0 times 0. So, and actually we did solve that by factoring. So that's your discriminant. So then what does this one look like on a graph if I were to graph it? Well, here's negative 1, negative 2. There's negative 3/2. There's 1, 2, 3, 4, 5. And since that's positive, it's going to open upwards somehow, some way. That crosses the graph twice. Okay, a couple other techniques. If I get just something like this, like instead of being like an ax squared plus bx plus c, you notice there's no like just x term. So basically it's like saying plus 0x. In other words, in this case, your b is 0. You can try factoring. You can try completing the square. You can try quadratic, all that. But easiest way is just, if there's no x term, just divide. So x squared is 3. Then you square root. And you're going to get both the plus and, again, when it's squared, you're going to get two answers. One plus, one minus. Now this one's a little harder. Let's take a look at that and see what I see. First thing I'm going to do is tell that 2, it's been nice knowing you, but get. So these particular problems are kind of like what you did when you did completing the square. When you got to where you had the square completed and then you went about getting rid of it. So I take the square root of 25, which is 5, and I take the plus or minus of it. You could say negative 1 plus or minus 5. And no, let's not do, because I can combine those. So you got negative 1 plus 5 or negative 1 minus 5. So you get 4 or negative 6. Kind of like that. Let's try this guy. Again, if you want to try and factor this, you're going to find it's not going to work well. So how do you know you can factor it or you can't? Well, I look at the discriminant. B squared minus 4ac is going to be negative 4 squared. 4 times 1 times 13. 16 minus 52, which is negative 36. Last time I checked, negative 36 is not a perfect square. 36 is, negative 36 is not. So since that is less than 0, I know I'm going to get two imaginary or two complex zeros. Or if you wanted to say no real zeros. Meaning what's going to happen? Well, this guy's never going to cross the x-axis is what's going to happen. But rather than saying it's undefined, let's solve. You can do quadratic form if you want. I'm going to do completing the square on this just because I think it's probably the one that maybe you guys need the most practice on. Actually, I'll do that in quadratic just for giggles. I'm going to move the 13 over, so that's negative 13 plus the box. So then, how do I find what goes in the box? I take my b term, And I divide it by 2, so I have negative 4 over 2. Squared, that's 2 squared, that's 4. This will factor as x minus 2, x minus 2. Negative 13 plus 4 is negative 9. That gives me x minus 2 squared is negative 9. And when I square root it, I get x minus 2. Again, the square root of negative 9 is 3i. But since I need 2 solutions, because that's my degree, I hit it with a plus minus. That's also why, like in your quadratic formula, it has that plus or minus. That's to get the 2 answers. So then I move the 2. And since they're not like terms this time, if you just wanted to say x equals 2 plus or minus 3i, I would take it. If you like separating them and saying 2 plus 3i and 2 minus 3i, I would take that as an answer too. Again, notice a plus bi, a minus bi. So when we say that you get 2 complex or 2 non-real zeros, they're going to end up being conjugates of each other. So kind of a cool thing. And that's that. I hope it helped.